So, good afternoon, everyone. Welcome to the Heidelberg Joint Astronomical Colloquium. Welcome to today's speaker, Ariel Goobar from the Oskar Klein Center and Stockholm's University. He will be speaking to us about charting new physics territory with time-domain optical astronomy. So, as you all know, in the time of LSST and these long-term time monitoring programs that are on the market and that will come, this is an extremely timely topic and has already led to extremely exciting results, and some of these we will be learning today. So before we start, a few words on the speaker. So Ariel comes from Sussex. He did his bachelor there, and then he moved quickly further to the right to Sweden, where he got his master's at Stockholm University and his PhD. From that, he moved further left again to California, to the Lawrence Berkeley National Laboratory. He stayed there from 92 to 94, and then he moved back to the University of Stockholm, and he is full professor there since 1999, so a long time. So he got many distinguished prizes for his work on high redshift galaxies, cosmology, and aspects of time-domain astronomy. Let me just add a few, or name a few. There's the Gustafsson Prize, one of the biggest Swedish prizes for young researchers below the age of 48. I mean, it's a question of how you define young. He got in 2007, together with his team, the Supernova cosmology project, the very prestigious Gruber Prize in Cosmology. Just recently, in 2015, he received the Breakthrough Prize in Fundamental Physics, again for the Supernova Cosmology Project. He is, since 2016, elected member of the Swedish Royal Academy of Sciences. These are just some of his distinguished prizes. So let's get to the science, and let's welcome Ariel.
Thank you. Well, thank you, Ralph. Thank you for a very, very nice introduction and the invitation to come here. It's a real pleasure to be here and tell you about something I'm really excited about, which is, as you alluded to, the prospects of doing new things in time-domain astronomy. So I'll get sort of to the punchline to begin with, so you see where I'm heading. So what is really new? As you know, as you heard, I've been working in time domain for quite a while. So why is it that I think now that these are exciting times? So the explanation has to do with technology, like always. So the new technology allows us to actually go from monitoring very, very, very tiny patches of the sky to cover essentially the entire visible sky from any given observatory. Once you start being able to paint the whole sky, you can also do different things. You can start looking at the sky at much faster pace. You can revisit the sky, the same patch of the sky, much more often, and maybe start studying phenomena that you haven't thought about before, because you didn't have the technology to do so. So I think then there is an interesting potential here to discover new things, and also very rare things. Once you start looking at many, many galaxies, of course, interesting things could happen occasionally, very rarely, but you get a chance when you look at many, many galaxies. So I will be alluding to some possible implications for astrophysics, for cosmology, and if time permits, I have also some thoughts about fundamental physics that these things could be touched upon. So I wasn't sure exactly who would be here, just to make absolutely clear to everyone what we're talking about. So I'll be talking about finding transient things in the sky, supernovae. So how do we find a supernova? Well, you look at an image in the sky, many, many galaxies. This is just one galaxy in zoom. We are zooming on a galaxy. And then you compare that image with this image of the same patch of the sky, but as it looked a few weeks earlier. Okay? And then you make the difference in pixel plane. And whatever is left there is what we call a transient. In this case, it happened to be a supernova. Could be many other things too. All right, so how has this thing been working? Well, it's been working very well, and as Ralph alluded to, I've been working with the Supernova Cosmology Project, And since this is sort of Nobel times, I was reminded of Saul Perlmutter's Nobel lecture 6 years ago. And this is sort of the way we were describing what we thought was excitement at the field back in the 90s. And just to put it in context when I'll talk about what we do today. Okay, so what Saul was explaining here is that we took some images, just as I was telling you, and then one lunation later, we came back to the same fields, and we're talking about some tens or hundreds of thousands of galaxies, perhaps over, that you spend a week staring at those, just to map the entire sky. And then you go back and you revisit. And if you're lucky, you would then see things like we just showed, and you would eventually build light curves. So you had the reference image back here, there was nothing, you come back, and maybe that's your first detection, and then you sort of allow enough telescope time to make a few data points, and ideally get a spectrum somewhere here where the thing is at its maximum. So the 2 points I want to emphasize that we're talking about fields of view which capture hundreds of galaxies at a time, and time scales which were about a month apart. Okay, that's where we were in the 90s, and I will be referring back to this when I tell you what we do today. So again, just to put it in historical context, within 3 or 4 minutes, I'll take you through a ride of 25 years of supernova cosmology that I've been involved with, starting with our first work with Saul back in '95, where we had sort of the audacity to put one data point here and tell, what did that tell us about things like, cosmological constant. In hindsight, it sounds kind of hilarious that we actually thought, we could put 1 point, but that was sort of we were kind of naive at the time, and we really thought that with a handful of points, we would actually nail this. Of course, as you know, 25 years later, we're still working at this, but that's only because what we found was pretty exciting. Surprisingly, if you look closely at the points, actually that data point was pretty much almost right on the money about what we think today. But with 1 point, of course, you couldn't tell. So let me then fast forward. This is then the competing team, the HIZ team. This is what they got the Nobel Prize for. When you look at this, it doesn't look very impressive. I'm showing this for the grad students in the audience. You might think that putting 16 new data points on a graph means very little, but if you're very lucky, it could actually take you all the way to Stockholm. So our team, we had a bit more data points. Now the key point here is that both of these teams were finding the same thing, that this data was suggesting that the expansion of the universe was not slowing down as everyone told us it had to do back in the 90s, but it was actually speeding up. So if I now fast forward many years, now you start seeing lots of data points. This is, of course, the kind of graphs you want to see. It's very convincing. This is Betul et al. And I'm showing you here because it also has interesting labels here. You have the Supernova Legacy Survey. This is it was a survey running from Hawaii. This is the SDSS, so the running also from the US. And these two projects found a lot of supernovae. And then there are a handful of supernovae here which are found with HST, and you might ask, why are there so few out there? And the reason is simply because the field of view, the camera on HST is so small that simply you're back to the story of not having many galaxies in your field of view. Over here is an interesting story that we'll be coming back to. This is called low Z, okay? So low Z doesn't sound like a specific project, and it is not. I will be coming back to that. So this is sort of a compilation of many surveys with very different specifications, and it has fewer data points over here compared to that. And that is because it's hard to cover enough volume if you're looking at the very shallow skin of the sky. It takes a lot of moving around your telescope. This is the data now. Now we almost make the full tour. This is the data that was in the archive a month ago or so. This is a work by Dan Skolnick and others. And what you're seeing here is all the data point here, and you see cosmology moving. And to make it a little bit easier for you to see, I've actually been the data. So you see that it's the lambda CDM, our cosmological standard model, is looking great. It's looking so great that it is becoming very frustrating because nobody wants this model to survive because it's a very unnatural thing to happen. This cosmological constant is just it has a very unnatural value. So there is a lot of discussion about how to deal with, how to try to understand what this dark energy is, assuming it is not cosmological constant. And if it is a cosmological constant, how do we actually get it, how do we make ourselves, how do we convince ourselves that that's what we got? So of course, in order to do so, one of the things we want to do is go to very high redshifts, and that, of course, that really forces us to work in the near infrared, and that forces us to work with satellites, because, of course, near infrared from the ground at this very high redshift is virtually impossible. That's a great topic in its own, but I will not talk about this topic. Instead, I will focus on the other part of the Hubble diagram in low redshift, because as I told you, what we had, there were not enough data points. Even if you want to anchor this Hubble diagram, what you find, surprisingly, is that what's limiting the precision is actually your lack of precision down here. So this is for getting dark energy. You've also probably all familiar with this famous now or infamous tension about the Hubble constant. There's some number that comes from the local measurement. There's another measurement that you derive if you're looking at the cosmic macro background and the baryon-acoustic oscillations, and you try to anchor back. And these two values of the expansion history of the universe differ by about 8%. I mean, a few years ago, being as close as 8% would have sounded, perfect. Why discuss about it? But now the precision or the claimed accuracy is so good that this is claimed to be a 3.5 or so sigma tension. But of course, the other reason we want to go here is not only to do type 1a supernova cosmology, but also to find more and different phenomena that we haven't thought about. Just to emphasize on the issue of what's happening down here, I mentioned that the data here is not one survey, but it's a compilation of surveys. And if you look closely at this data point and you bin it, as was done by Skolnick et al., something kind of funky happens that if you only look at the statistical uncertainties, the quoted error bars, there is something very, very funky going on here, which may be boring systematics or could be some interesting stuff. I don't know what the answer is, but certainly motivates me to go back and get a good look at that data. I mean, get a look at that, not that data in particular, but get data in that wretched bin range, because new things could happen. All right, so I've tried sort of to explain to you that there are good reasons to look at the sort of low redshift universe, and the reason we can do it now is that whereas in the 90s we were working with cameras which had only a field of view arc minutes, now we're on the many, many square degrees, okay? So this is what I was alluding to, that we can get large statistics and get interesting and rare phenomena. And I will emphasize on an example later on in my talk. So the other implications, as I also mentioned, is that the field is moving towards, not like we were doing back in the supernova cosmology time that we were in the early days, where we were sort of taking an image and then waiting for a full month before we get an image. Now we want to find the transits while it explodes. We want to find it on the same night, okay? So we want to go much earlier. So that means that we will capture the phenomena we are interested in exactly when they happen, and maybe learn about the physics of that phenomena. And also we will also find new things which we may or may not have thought about, but things that vary on a much shorter time scales than this type 1a supernova that have nearly 3 weeks of rise time and then be longer fall time. So we might be looking for phenomena which maybe have a day or so of rise time, and I will give an example of that. All right, so the project I've been involved in the last few years is the Palomar Transient Factory. In fact, I've been involved in the intermediate Palomar Transient Factory. The Palomar Transient Factory started in 2009. I got involved in 2013, and it's a project we just finished. We are working on the data. I will just showing you, I will not show you the entire data set. I will just show you some examples of how cool the data is. And this is a project based at the Palomar Observatory. This is it's 48-inch, it's 1.2 meter telescope, which is completely robotic, that we use to scan the sky. And there are a couple of telescopes which we occasionally use to get identification. What is it that we found? We find a transient, and then we want to see what kind of transient it is, and then we have these bigger telescopes to get spectra. This is an important thing here which makes these projects exciting. With LSST, for example, there will be amazing amount of things vary in the sky. But there will not be that many bigger telescopes around from which you can get a spectrum and get the light result and the wavelengths. Here we have the luxury that we have much bigger scopes, so we can actually go back, and things we find here we can easily observe with a much bigger telescope spectroscopically. So this is sort of what the current field of view, or the project we just finished, the field of view. You see it's about 7 square degrees. This is what they looked at. Conveniently, one of the chips broke towards the end, so we could nicely fit in the moon there to show you how big the thing is. And this is just, again, for the sort of young students to get an idea. This is sort of between, this is what when I started working in this field, this was considered to be a big camera, and you see this is now more of a state of the art. And once you get a big camera, not only do you want to find things early in the data and only find out about it, like a week later, you want to find things as they happen, and that puts a lot of pressure on software. Okay, it's not only just getting a nice robotic telescope, you need to have your pipeline there, so if something goes bump in the sky, you want to know about it within minutes, if possible. So that's what actually was one of the strengths of the IPTF. So just to walk you through here, we got the data at the observatory. It was actually shipped to Berkeley, where there was supercomputers that could take care of this. We compared it to images, just as I showed you in my first slide. We look for the differences within, you see, this is the time between the things. So within 5 minutes, we had sort of digested the image. We knew what the new potential discoveries were. And here again, once you have such a big camera, you have image defects like the one up here. So you cannot afford to have a human being just going through all of these, tens of thousands of things that are flagged as a difference. You need computers to help you with that. And there's a lot of machine learning went to sort of cut down the false positives down to a level that a human being equals a grad student, could actually look at the images in a place where it's daytime, where the telescope is taking data. So this is very convenient. There is a 9-hour difference between Palomar and Stockholm, and yet another hour between Stockholm and Israel, the Weizmann Institute, where our colleagues are sitting. And so we had people then, the few transients that the software told us that the machine learning and everything had told us, at least please take a look at this. We had our young colleagues looking and triggering follow-up resources when deemed interesting. But the whole process, it was sort of a 5-minute thing, okay? So, so then, sometimes we could find things like this type 1a supernova. We found it about 50 times fainter than the peak. And we could trigger all kinds of resources, including space, spectroscopy, radio, you mentioned it. I had the slide with all the things we triggered, but in order to keep going, I'm not showing that. But the point is that this allows us to study things very early on in the multitude of wavelengths and instruments. So one of the things we have been looking at, there's this question about for example, what are type 1a supernovae? So we're looking for evidence that whether it's a sort of a white dwarf accreting mass from a bigger donor star, or is it sort of a collision between two white dwarfs, or is there a circumstellar medium around the supernova, so on and so forth. Things that you have a chance at least to study, to address, if you get to see the explosion from the start. And it gets more and more difficult as you catch it later. So another example where we found it very early, and I want to emphasize the work with Marcus here. This is type 1a supernova 14J. And this is really, you can really argue that we saw this thing while exploding. And here we got a bit of help from this. This is sort of, again, a small robotic telescope, just happened to be looking at the right place. We cannot take credit for that, but they actually did get the data. And this sort of, it just shows you how beautiful the data set you can acquire if you're just reading out on the right location at the right time. And again, these observations have allowed us to come to the conclusion that, unlike what we thought, 10 years ago, and people here will comment on this as if but we now are no longer sure that the normal type 1a supernovae need a different explanation. So the bulk of the data might be all explained by the double degenerate channel. So, back 10 years ago when I talked to my fellow theorists, most of them used to tell me, at least up to Earth, that the single degenerate channel would seem more natural when you have a bigger donor star. But now, all the data we see, we don't see any like bumps early on, etc., that would tell us that the explosion, sort of the ejector run into the remains of a neighboring star, etc. So there is a lot of data, a lot of studies that we and others have been doing based on early data related to that supernova, and again, the fact that we found it earlier. We could also trigger, as I said, follow-up observations. In this case, we made a very intriguing study of using, from the near infrared, to the near ultraviolet using HST. We studied the extinction. This supernova happened in a very dust-rich, it happened in M82. It's a lot of dust, as you can see, and there was a lot of attenuation. Now, the thing we very easily could establish that the kind of extinction law that we see for stars in the Milky Way, well, that was nowhere near our data point. This is what I'm showing you now. Instead, we found that it's a much, much steeper extinction law, and we're actually still struggling to understand why that is the case. I've been working for many years investigating the hypothesis that it could be circumstellar dust, so multiple scattering of light around the supernova. I'm no longer sure. I'm no longer putting my money on that's explanation. If there's time, etc., we can discuss that towards the end of my talk. So let me then tell you more or less where things were with the IPTF. So we found an amazing number of type 1a supernovae, a bit over 2,000, a huge number of core collapse supernovae, and you see sort of for the type 1a supernova redshift range, you see we were sort of peaked at somewhere of redshift 0.1 or so. Okay, that was sort of most of our data was. Here's some specs. So we are on each field for 60 seconds, and the pixel scale is about 1 arc second. 1 arc second pixels. Okay. Now on October 2nd, 2016, something very, very unexpected happened. I was at home, kind of bored because my wife and I were supposed to go to the French Riviera. For boring reasons, we could not go there. So I'm looking at the data stream coming from the telescope, and something struck me as very, very remarkable. So we got a spectrum from this 1.5 meter telescope, the one on the top here, and I've been staring at long enough. I'm not, I wouldn't call myself an expert on spectroscopy, but I've been staring long enough about at supernova spectra that I immediately saw that, wow, this obviously looks like type 1a supernova, but that's at a completely different redshift than we're expecting, not at all at the 0.1 redshift where we find things. Not only was it that it seemed ridiculously distant in terms of redshift, it was very, very bright. This was not like close to threshold. This thing was like almost 3 magnitudes brighter than what we would trigger on. I said to my colleagues, this is so weird. Please get me another spectrum. So then we went to the bigger scope. This is from the 200-inch telescope. And then again, sort of the wiggles looked fine. And just to tell you how fine it looked like, so this is the sort of a vanilla type 1a supernova type 1a supernova 11 Fe at about the same epoch in time. You see all the wiggles match. So there was no question about that this was a type 1a supernova. However, it was at a redshift 0.4, okay, which was nowhere near the map for what we normally do with this instrument. So then all my alarms went off. I said, this has to be lensed. And indeed, looking at the details of the spectrum, we started finding lines at 2 redshifts. One, from the host galaxy at exactly the redshift where the supernova was, 0.49. But we also found lines at sort of an intermediate redshift, which sort of hinted to us that this light was actually going through a galaxy, and that galaxy is probably magnifying what we see, the light we see. And indeed, so just to give you a sense, so this is sort of the light curve of this object, and this is where we expected the light curves to be in different filters had it not been lensed, okay? So there was a wobbling, 30 standard deviation offset from what we, the brightness of this object had it not been lensed. So we immediately triggered, contacted HST, said, please, you have to look at this thing. Every colleague in Hawaii, and ESO, do you have a telescope with adaptive optics? So we did get time with the HST, and this was very exciting. This was right around the time when there was this nonsense. It was the American election, and all these nonsense tweeters were coming out. So for once, I was very happy to see a Twitter that actually seemed to have good news. So I was very excited, and then the data came. Okay, I could almost not hold my breath, and then the data came, and it's like all black. I just said, oh my God, we blew it. So something terrible happened here. And then I'm going around with DS9, looking around, and at the end of the chip, I find the thing. So I almost got a heart attack. And it sort of turned out that it wasn't actually our fault. It turned out that the operators of Space Telescope had picked a guide star which had a huge proper motion. And they told me, oh yeah, by the 5th visit we will change this. I said, no way, you change it right away. The next visit the thing has to be centered. And actually they did. So all the data they followed was great. But that was a pretty scary moment. I want to think about what would have happened if this thing would have moved all the way out. Anyway, so eventually it was a happy story. We had got nice data from HST. We got nice data from the ground, from Keck. We also got data from BLT, however, not at the resolution of this thing. And the point I want to make here is that we out of this ground-based data with very this is sort of the typical seeing at Palomar. We could actually resolve something of this. No, we cannot resolve it, but we can actually tell. We can get convinced that it has to be something like this, okay? A quadruple lens in this case. Of course, we couldn't tell it was a quadruple lens, but we were pretty sure it was a lens system. So, and we're right now in the process of analyzing the HST data that follows, so we will be able to make a time delay measurement that, this is sort of in the context of the Hubble constant. Now, so this is sort of a zoom on what we found. And I want to sort of try to really make a point about this, that we had a telescope not far from Los Angeles, in one of the worst sites you can really imagine having a telescope. And typical thing is 2 arcseconds, if not worse. But yet, we were able to say, I think there's something exciting going on here, and then trigger a high-resolution imaging instrument like HST. So it was actually the time domain data, time domain information that gave it away. This is very important because imagine you try to find something like this only using HST. Well, you would never do that, right? Because this is, you would have to this is a very rare thing. You would have to look at so much of the sky that the nights would never be enough time to map big enough chunks of the sky. Whereas with the project I'm just describing to you, with the time domain information, we know right away where you should look. And of course, this is something exciting if you want to find many more strong lens systems as this one. Now, there is a lot of questions one might have about this one. First of all, it's a smaller time, it's a pretty small physical scale, and that has to do with the fact that with our supernovae, if I see the lens, it doesn't really matter how small the angular separation is. It could be microlens, it could be just on the same spot. I would still flag it as interesting. So this takes us to a new regime where we can start studying strong lensing at physical scales which are smaller. Smaller than the ones people have been doing with quasars, for example. If you look at the quasar, the hundreds of strongly lensed quasars there is maybe 1 or 2 which are at this angular scale, but normally it's very much easier. But with supernova we can find them without any effort, as long as we look in the sky with these cameras. The other thing which we're working on very hard now is that actually there is a fantastic symmetry space-wise here. So we have almost a perfect Einstein cross. But as you can see for yourself, the brightness of the images are very, very different, okay? The multiple images, naively you think, well, if it's a perfect symmetry, then they should be equally bright. Of course, then you have to account for extinction, okay? So we're now in the process of doing the extinction very, very carefully. But I can already tell you the answer. The answer is that it's very surprising that this very is if you only take the smooth matter that in the lens itself, you would never get this very big difference in the images. So you need additional microlensing, so additional objects that sort of focus the light here without breaking it up in with an angular separation which is small enough that we cannot actually resolve this. So this is sort of exciting at times where there could be stars, of course, but it could also be, this happened at the same times where everyone was talking about, what is the LIGO data telling us about all these black holes. There could be some contribution of, for example, black holes that could be responsible for the microlensing of this thing. Of course, there is nothing there that tells us that has to be the case, except for a little hint here. I'll tell you a little bit of a hint, which is, if you try to, not focusing on this specific example, but if you ask yourself the question, all right, if I'm looking at all the sky, okay, randomly, not necessarily looking at the locations near a core of a galaxy, how likely is it to find a supernova within the redshift range we're talking about here, within redshift 0.45 or so, with a magnification of 16G, IPTF 16G? Well, if you only look at smooth matter, well, that's really not going to happen. If you start adding graininess, in this case, I'm adding sort of fraction of the dark matter, so some of it could be like 10% of dark matter could be black holes, where then you start building up a tail that all of a sudden makes it not at all not as unlikely. Okay, of course, it would be much more likely to find something over here. Why we have found something at magnification of 50 or something instead of 5 or 10. That is, maybe we're just lucky, or there could be something profound. Now, so what I will be, I don't know. I sort of leave it open as an interesting scientific question, just for people. There's been a lot of debate in literature in the last few weeks as to is there room for things like primordial black holes or not. And people are arguing that something like 10% or so of dark matter could actually be in the form of compact objects. In fact, there was a paper even more recently, I think a week ago, by Paul Schechter, who's even suggesting that a 10% fraction of dark matter in compact objects is even preferred by the microlensing of quasars. I don't know. We'll see where that goes. My only answer to that is we need more data. Okay, we'll see. So with next, let's see how I'm doing time. The next, what I will tell you is the future. Okay, the future, from my point of view, is what we'll be doing with the next generation of camera in the same observatory where I just showed you at Palomar. We just changed the camera to another one, and we conveniently changed the name to the Zwicky Transient facility. And as we heard in the beginning, LSST is coming. We're just running ZTF just until LSST starts, and then of course LSST will take over. But we hope to do a lot of bread and butter and find a lot of cool things in the period between now and LSST start. So how big is then the Zwicky Transient facility? Well, we just had first slide, so you're looking at the first image of Zwicky. It's 47 square degrees. This is what we used to have, okay? You see the indifference? This is, by the way, for comparison, you have other instruments that you might have heard about, Dark Energy Survey camera, this is a Subaru, Pan-STARRS, and LSST. So this thing is bigger. It's bigger. Of course, it's a smaller telescope, okay? So there's some trade-offs up here. So we have first light, and just to give you a rough sense, it's not only bigger, but it's a better instrument. It's a better CCD, it's a better readout, shorter readout. So we are effectively 12 times faster than we were with IPTF. So whatever we could find, once in 10 years with IPTF, we should be able to find it once a year here, okay? So I'm pretty hopeful that we found one lens supernova, and who knows, maybe there were more there that we just were not prepared to find. But there is some expectation that we could find maybe 3 a year with ZTF. We'll see. So this is, I don't know if you see from the back of the room, this is sort of an animation made by Rahul Biswas. What you see in the dots here are, this is sort of one night. You see just the time clocking, the time ticking, and the dots here are live supernovae, live type 1a supernovae. You see here is sort of a mock of how the camera will be looking around in different filters. When this thing changes color, it means that we change filter. There are 3 filters envisioned here. And what you see here, that everything the camera is looking at some spot, there is about on average 3 or 4 such dots, okay? So every time we point at somewhere, there's going to be a live supernova, okay? So it's going to be a lot of supernovae, and sort of the redshift of the supernova down here. So you know, this thing will be drowning in supernova data. Okay, that's the thing I'm showing you. So there is, as you see here, some of the times we're pointing at the galactic plane. So in this project, this is not only about transients. Many of the people in the collaboration are interested in variable stars. Okay, so there is a galactic plane component as well. Okay, so in a year we are counting on having, you know, nearly 900 type 1a supernovae for which we will get a spectrum. It will be maybe more, or definitely many more, that will be too faint for us to get spectra of with our current resources. Again, I'm reaching out to people here who might want to, you know, say, oh, I have a telescope, you know, why don't you send us some targets and we'll type it for you. Well, we'll love that because we'll have way too many things compared to what we actually can digest on our own. So any suggestions will be very positively received. And as I said, if we just scale based on what we've learned since the analysis of IPTF6NGU, we think there's a good chance we can have 3 a year. This is for a 12-month period. Okay. The other thing, of course, is very timely. I just came from the Nobel party. The new horizon is obviously the world of gravitational waves, EM counterparts. We've seen black holes. We've seen neutron star mergers. Of course, the next thing is some mixing, and it could be new phenomena. And in Stockholm, we just have we've been funded to have a nice research activity with synergy between the theoretical work of Stefan Rosvåg, who does a lot of modeling about exactly what happens when these neutron stars or neutron star black hole merge, and all the interesting things like the production of heavy nuclei and so on and so forth, and how they look then in the sky for us looking at the variable sky. So these things are sometimes called macronovae or kilonovae. The point is that now we were speculating for a long time how these things look like. Of course, as of August last year, we sort of know how at least one of those looked like. This was the famous GW170817, which happened in coincidence with GRB, and then of course, there was this time coincidence, was a spatial coincidence, and then soon after, I think a third of the astronomical community of the world was actually staring at this thing, and so were we, and then this thing was found. And the point I want to make here is that the error bar, this was a particularly good, successful, was a particularly good event in the sense that it was extremely nicely localized. It was only 40 megaparsecs away. It was too good to be true, and I'm not sure how the next round of events will look like. The only point I wanted to emphasize is that if they're all as nice as this one, then one pointing is enough with our camera because we cover that field, okay? I don't expect things to be that easy, but still tells you that it's a nice sized camera for this kind of science. All right, so I was alluding to the fact that in the past, we have not been sensible to, we've been sensitive to things changing this fast. In fact, if you look at the event we just witnessed, for practical reasons, people were not, this thing happened when it was daytime. It was seen, this thing was, it was sort of a very unpleasant place to find a transient. It was very near the sun, etc. But anyway, it took 11 hours before people could actually point their telescopes and find it. And after 11 hours, it had already started to fade in the optical. Okay, in the near-infrared, it actually went on for a while, but in the optical, and I'm sorry, it's probably hard to see exactly what those bands are, but if you see in the optical, something like here, this is sort of an extrapolated peak. The peak happened definitely within 12 hours or so. Okay, so if we want to study transients like this one and capture them in detail, well, then obviously you need very fast cadence. You need to not only, you need to point, of course, as soon as you can with a LIGO trigger, or just look for these things without a LIGO trigger. But the point is that if you want to get points on the rise here, you need to go much more often than just once or twice a night, okay? So, in fact, there was this nice work by Dan Skolnick. It was actually different. It's the same Skolnick, but a different paper than the one I was talking about in the beginning. he actually went through, and he and a large team of people, I should say, went through previous large surveys, including the ones I was showing to you, like SSS and SNLS and PanSTARRS and DS and so on and so forth. And the point is that these experiments, these surveys, were not scanning the sky with the necessary cadence to capture this thing. So even although these things surveyed the sky for many, many years, and collectively, you know, they only had like a 10 or 20% chance to find one such event, okay? Whereas things like ZTF, the approach I'm talking about, I'm not talking about LIGO saying, look there. I'm just saying that this thing is just scanning the sky with the cadence we have decided. We have a chance to find 10 such things, even if LIGO is off, okay? We'll just be seeing the optical counterpart. It will be not as much fun as seeing in coincidence with regards to waves, but I'm saying we can actually study the population even when LIGO is taking a rest, okay? So that will, and of course LSST will yet, you know, increase by a factor 7. But again, it's one of these things where the jump between ZTF and LSST will not be, you know, will not be amazing, no. So let's see, now is the time where I'm looking at how many minutes do I have? I can do, okay. Then I'm going to go really crazy here, okay? I admittedly, I am a physicist by training, so I'm really keen, I sort of have this keen interest in fundamental physics. So I asked myself the question, okay, these are all the astrophysical phenomena we are all very excited to do more. What about the really, really weird things, okay? So I'm going to talk about exotic transients. So one of the things which I find very truly fascinating, and you know, I wouldn't bet neither my car, nor my laptop, nor my wife that exist, they are the things called cosmic strings, okay? But I think it's very exciting to look for them. These are there are topological defects that if they happen very early on in the universe, and they just constitute a relic, sort of a defect from the early universe, and they just might be floating around all around us, but there are very few ways to tell, okay? The point is that these are things that interact extremely, extremely weakly, and you know, there could be 10 to the 5 cosmic strings in our galaxy, and just we wouldn't know unless we see something very bizarre, like a microlensing event going through one of these ruptures of space-time that you see an object and then you see it twice. Okay, what happens is that you can, if you have a string going here and you're looking towards a star, as the string happens to pass by or the star happens to move across the string, the light would actually go 2 ways, and you will see an exact doubling of the image. Okay, this is very different from any microlensing caused by a star and so on and so forth, because then it's sort of an arbitrary amplification. That, you know, it's sort of this one is called binary, and there's talk about binary microlensing because it's either a factor of 2 or nothing. Okay, modulo, of course, some spatial effects and your sampling and so on and so forth. But we have a nice chance, and we're working right now on there is a nice, well, there are lots of theoretical papers by Chernoff and Tai, and we are working with David Chernoff at Cornell to figure out what are the chances to actually find one of those events when staring at Andromeda. It just happens that my little claim in this business is that by reading the papers of these characters, I realized that they have actually been thinking of the wrong place to look at the telescope. Andromeda is actually a sweet spot to look for these things, because then you have sort of the halo of our galaxy and the halo of Andromeda, and there's a lot of geometrical things that makes this very, very optimal. If these things exist, then we should have a chance to find them. Now, there are, of course, free parameters in the theory, and I'm not going to bore you with these parameters. The only point I want to make is that these microlensing events, if they happen, they are very, very, very short, okay? So the things we've been doing up to now, they don't cut it. If you want to find these microlensing events, not only are they only a factor 2, but you typically have a duration which is shorter than a minute, okay? So it could be that if we change our strategy and stare at nearby galaxies, as Andromeda I mentioned one, or even also at the center of our galaxy, from another location, of course not from Palomar, then we may be able to, you know, open a new frontier, discover early universe relics within optical astronomy. That would be sort of a new concept. Similar things have been actually postulated by other people, that there could be things like, there is a dark matter candidate called the Axiom Particle, being suggested by, among others, Frank Wilczek, who is now a professor in Stockholm. So we get all charged up in Stockholm talking about axions. So one of the things that people are talking about is that there are axion experiments where they look in the lab and see whether there is sort of, you have a cavity and you're looking for interactions with an axion with a magnetic field, which creates a photon that, radio waves that you can detect. But of course, that only happens if axions move as free particles and heat as a lab. But some people have been arguing that, well, you have to worry about that these axions might actually cluster. Okay? So if they cluster into bigger structures, then these things could exist and they will just never pass your lab experiment because they are not moving freely the way you thought about. So there is a complementary technique that you need to worry about is say, what if they cluster when, again, the same story is there, that these things will make up clumps of matter, of axion matter that will be extremely light, and these things will generate, again, microlensing events, which are just way too short to be limited by what, for example, the Macho collaboration or the EROS collaboration have done. So again, there is some room for there's some room for what other telescopes could do. This is actually work with the Subaru telescope, and this is what we hope to do with ZTF. The point here is that how many such microlensing events would you find, assuming, and this is a big, if all of the dark matter is in axions and it's all clumped, then we'll be in the hundreds. Of course, I'm just painting what would be the most rosy outcome. What this really means that if the axions are clustering this way, they could even make up 1% of the dark matter, and we might still be able to see it. Okay, so I think I'm getting to the end here. So just to essentially recycle my first slide. So what is new? Well, I think what is new is that technology is pushing us towards trying new things in time domain astronomy, looking at bigger parts of the sky at any one time, and revisiting the sky much more often than we have done in the past. There are new phenomena I mentioned. There could be short-time microlensing. Of course, we will be seeing, as you saw examples of the onset of supernovae, and learn much more about what is that exploding, and whether it is actually okay for us to use them in cosmology. Up to which precision? The question is, up to which precision can we trust, for example, type 1a supernovae standardizable candles? We might be start seeing diversities here that we need to actually worry about. This is sort of the 1a systematics. I showed you one example where we found a type 1a supernova which was lensed. We are now working on, what could be a new way of measuring the Hubble constant. Again, I don't want to oversell this. I'm not sure if this is I'm not sure by the time we do this, the Hubble tension might already be gone. So I'm not sure how much I should get excited about it, but it's certainly a new way to look at the Hubble constant. Which complements, by the way, what people are doing already with quasars. I don't want to, again, it's not completely new. It's just that we have a standard candle to do this. I mentioned that once we start looking at new timescales, or we need to start sampling the sky at new timescales if you want to capture things like the rise of a macronova and see what happens at the onset, see what happens on the rise. That will help us to tell, what is the diversity among macronova. And there's a lot of debate about, are these the sites where we synthesize the heavy elements? It certainly looks like the way, but in fact, one of the puzzles we had with this particular event is actually, if you look at the rate and the amount, on the power it put out, it would seem to overproduce the amount of heavy elements. So probably the rate, that one was probably an oddball in the sense it was probably either too bright or just most of them do not happen that often or are not so bright. So we'll see. We'll need to sort of collect statistics to see what happens. So the only thing that's limiting us, I think we're in a very good path to start our survey. So we start our survey in February. Right now we are in commissioning phase, just getting all the software up and running, understanding all the, all the teething issues with the instrument. And, but once we're up and running, what will really be the bottleneck is our ability to follow up all the things we'll be finding. We'll just not have enough resources. So, whenever I go and say, if you have a telescope and you want to be part of this ride, just talk to me. I'm sure we can. Come up with something. And even more exciting from my point of view, if you have, after listening to this, you find that there are more exciting things you could do with such an instrument. Well, please let me know as well. So I think I stop there. Thank you.
So, thank you, Ariel, very much for this exciting overview of time domain astronomy, what has happened in the past, what is currently happening, and what will come in the future. So, the podium is open for discussions. We start with Stefan, and then we move to you.
You have shown a light curve of a supernova from which you concluded that it favors the double degenerate scenario. Can you repeat the argument why this favors the double degenerate scenario?
Actually, what I was showing here is one example. I think maybe not even the best one example, but it's one where we worked on here with Marcus. So there are a few arguments. First of all, for example, there are arguments. Let me just go to the right page here. Okay, here's
this one.
Yeah. So there are arguments. For example, there was like a supernova before this one. 2011 FE, where we had exquisite images of HST, let's say, before the explosion. That's true for this one. So you could not see in the pre-explosion HST images, you did not see, let's say, anything that looked like a red giant in that location of supernova. That's one thing. The thing I was alluding to early on here is that in the single degenerate scenario, there is expectation, in particular in the UV, that you create early on where there's very little of the energy going into powering the light curve from the radioactive decay, that you could actually get shock heating either of the outer layer of the white dwarf, which is of course very small, that would not count, but you could get heating of the outer layers of the material from the companion star. Now, we didn't see anything of that in 11 FE. Here, actually, I have to say that we saw some bump here, but also subsequent work by Marcus and colleagues shows that there's a lot of things going on early on, and whatever we saw, we certainly did not have to invoke a single degenerate to explain it. Then going into what many people have done, so people look again, both sort of radio, again, once you have having this collisions, you expect radio, X-ray, at late time you expect to see, for example, H-alpha, hydrogen from the companion. None of these things have been seen so far. So it's not conclusive, but certainly there's nothing that we can say, nail it, that here's a case where we are sure it's a single degenerate. I don't think that for normal 1As, I'm not sure that's been shown. Therefore, I think it sort of smells to me like the bulk of the normal 1As are probably in the double degenerate. But I have some people in the front that might want to comment on that.
I have a quick question concerning more observations in more shorter time scales, like minutes, for example, or seconds. What could you say about interesting objects and maybe ideas concerning fast radio bursts, for example, concerning maybe some optical emission if it happens within the galaxy?
Oh, well, I mean, I mentioned a few things that I'm excited about for short timescales. The one thing, actually, just since you're talking about practicalities, let me say one thing that limits the practicalities right now, which is the readout time, okay? So, again, so sorry if I become boring technical now, but one of the things let's see, where do I have it? Okay, never mind. We have it right now. What limits us is a 36 seconds readout time. Here it is. We have a 36 seconds readout time. So whether we would like to go more often than that, with this instrument we cannot. With ZTF, we have a 10-second readout time. So that already pushes us. With LSST, it will be a 2-second. LSST, I love it. That's good. Now, so all of the things you mentioned sound very exciting. Now, fast radio burst, yeah. I mean, these are the things that people will try to nail. I don't know what are the prospects to see something in the optical. I don't know. I'm certainly not an expert, but That's, once you have a cool instrument, that's what we will try to do. Obviously, whenever something exciting happens and we have a chance to stare at it with our instrument, we'll go for it. But if you have any good ideas of, I think I mentioned a few. You mentioned fast radio burst. I don't know what else is out there that we should try to go for. But again, the only limitation is how deep we can go with a 1.2 meter telescope, which is typically 21st, 22nd magnitude if we push it, and the readout time is 10 seconds. So anything that happens with much shorter than 15, 20 seconds, we're not going to get it. Yeah.
What you unavoidably will see is a lot of stellar microlensing. And what you also will see is a bit less, but also microlensing by planets, if you're quick enough.
Yes.
And you will be. Now that was not new, but if it is true that what some people say, that probably we even have more free-floating planets in our Milky Way than stars, then you might look, and you might also see microlensing by free-floating planets. That is a microlensing event in a star that does not undergo a planetary that is not undergoing a stellar microlensing event.
Right.
So be aware. That is one answer to your question.
Absolutely.
What else to look for?
You're absolutely right. And in fact, one of the things, yes, and so we don't have enough microlensing aficionados in our team right now, in fact. So absolutely, no, we are aware of that one could do things, but again, there's so much science and we are a limited team, but that's a good maybe a good thing to start discuss for the future, yes. But we'll be looking at the galactic plane, so certainly we'll be looking at the Milky Way, we'll be looking for, these things will be in our data. The question is, will we be able to pick them up? That's the question, yeah.
When we talk about time domain astronomy, for me there raises the question, what about completeness? Is there anything in the range of completeness correction that we can say, okay, so many supernovae have been detected, but what about those who have not been detected? And even more for optical counterparts or for electromagnetic counterparts for gravitational waves, where people already draw conclusions from just the number of events that have been detected so far. Is there any kind of completeness correction for time domain?
You are right on the money. In fact, so one of the big failures from my point of view, I completely share your view that's overlooked very often. So one of the big failures with this survey is that we could not do this because we cannot do what you said because we kept changing the survey strategy. We kept making it very ad hoc, which objects we typed. So for IPTF, we can only do very, very rough estimates of our completeness. For ZTF, we have that in mind from day one. So we've been thinking about it very, very carefully. We're thinking about exactly how we will keep the history of everything that varies in the sky. We're doing a lot of more databasing and archiving in a way that we can go back. And we're not going to change the survey strategy for a year. So we want to make sure that we don't keep moving things around, because that becomes a nightmare. Now, if you 1 month revisit the sky twice a day, and the next month you do it every 3 days, it becomes very hard, and then the weather comes in and you didn't actually quite keep track of when did it. So in my mind, one of the biggest goals with ZTF, since we will have so many transients, we'll be able to do rates carefully. And we are talking about having completely robotic thresholds for how to get spectra. So whenever something goes beyond 18.5, for example, we get a spectrum. No human being trying to decide whether I think this is too close to a galaxy. No, none of that. Just at least have surveys where we can say up to some magnitude. At least we and enough. Then of course you have to correct for weather, and that's unavoidable. But we try to make studies where we work. It's our goal at least to have sufficiently quantitative studies, well monitored, and nice databasing of exactly all the conditions that we can go back after 6 months and say, I think the rates of these kind of events is this, and we will be able to tell that. That's a hope. But with the current data, it's a struggle, I would say.
So let me also ask a question. In a sense, you are sensitivity limited by short exposure times and by the size of your telescope.
Yep.
And so I'm wondering, couldn't you go into space? I mean, I'm specifically thinking of WFIRST, and couldn't you think of a high cadence survey, just, I don't know, put in a few weeks of high cadence, large-scale observations? Would that be helpful?
Yeah, so I mean, WFIRST, it's, I'm very excited about WFIRST. It will only happen in 10 years from now.
Sure.
So I think everything you said is probably yes and yes, but I wouldn't say instead. I think by the time, my hope is that by the time WFIRST is launched, we will have a much improved understanding of the rates, for example, how things vary in the sky, so we can actually do what you said, an efficient study of transients at different timescales from space. That will be wonderful. But then, of course, WFIRST is a very political entity, and as you know, for example, ESA is not. As Europeans, we may or may not. We have to knock on the door, and we may or may not be let in. So it's. I hope we get there, but I'm not sure whether it will be feasible. Yeah.
Okay. Good. So, Herr Schatz is next, and then Herr.
I have a technical question. What fraction of the data which do not show transients do you store? Or do you throw them away immediately, or how do you do it?
So everything is stored. Everything is actually stored at IPAC. So everything actually, by the way, all the data from this survey is public. You can go and download it tonight. So it's all stored. I can, if you're interested, I can actually send you the link. And ZTF, maybe I should emphasize that it's sort of, there are three stakeholders. So we are a group of partners, 10 institutions that we own only 40% of the survey. Another 40% will be owned by the American Astronomical public. Everyone, it will be public to every astronomer in the US, and I don't see how they will block Europeans from just downloading the data. So in principle, 40% of data will be transient and static. Everything will be public, and 20% Caltech keeps for their own. But all of this actually, whether you get the data right away or you want to go and look at it later, it's all going to be public. And this data is public already. Yeah.
And 20% are those containing the transients?
Say it again.
And the 20% are those containing the transients?
20%. No, what I meant, I'm not sure if I got it wrong, but I would say that the survey of the time, so for example, what Caltech does with their time, I don't know. They can do what they want with the time. I just told you what the partners, and I know what the 40% public thing will do. Caltech might do whatever they want. I'm not sure. In fact, at Caltech there's a large interest in, actually it might be exactly down your alley, because at Caltech there's a lot of variable star people. They want to look at the galactic plane, so maybe those are the people to talk to. Yeah.
Another technical question to the Zwicky survey. How do you select the positions which you look at in a certain night? That's the one question. And the second night, how often are you repeating the observation on what time scale?
Very good question. All right, so let me tell you the strategy. So again, since there are 3 owners of the data, I'll tell you how, again, Caltech, I don't know. It's their faculty that they work with. I can tell you what 80% of the survey. So the 40% that we, the partners, these 10 institutions want to do with, no, let me start with that. Let me start with the one that NSF is paying for. So they want to do essentially, it's going to be 15,000 square degrees of the sky in G and R every 3 nights. So it is sort of, the idea is to make a mock LSST. Okay, LSST will do that. Sort of going back, essentially, do essentially all the sky which away from the galactic plane and away from the moon. That's about 15,000 square degrees. And then it will do a sweep of the galactic plane every now and then. Okay, but it will be essentially 15,000 square degrees in GNR every 3 nights. With the partnership time, and we only have decided for year 1, we will do half of that sky. We will add 1 more filter, I-band. With I-band, we will get a 3rd filter for half the sky. And then we will go high cadence with 1,600 square degrees. We'll be going multiple times in the night. So it will be a smaller chunk, but we'll be going multiple times. So we'll get at least 3, but most often 4 or 5 visits a night. That will be depending on the weather and how long the nights are, which season. mostly G and R, mostly G. Yep.
Good. I see no more hands up. So with that, let's thank Ariel for this very nice and exciting talk.
Thank you. Thank you.